Good morning, everyone. My name is Sanjeev Heda. I'm a principal industry consultant with SAS in our Internet of Things division. I appreciate the opportunity to speak to you today in person. It's been a couple years for me on this topic of how to operationalize and scale analytic pipelines with computer vision at the edge. A little bit about myself. I've been with SAS for about 4 years with the focus of providing thought leadership to drive advanced analytic solutions. And I have a specialized focus on the industrial and transportation verticals. Prior to joining SAS, I was with GE Power for over 10 years, where a lot of my responsibilities was delivering analytics to enable predictive maintenance for power generation assets. And for my educational background, I have both a bachelor's and master's in mechanical engineering. So you all may not know who is SAS, so let me describe who we are in 3 areas. First, our resume. We're an analytics software company, and that's what we focus on, is analytics. In the latest IDC market share, SAS is ranked #1 in the advanced and predictive analytics space as the market leader. And we've been doing this for over 40 years. So if you see those farmers commercials, right, we know a thing or two because we've seen a thing or two. That's us. But at the same time, right, in 2021, SAS was recognized by Fast Company to be on their list of most innovative companies. And I think that's an important testament because even though we've been here for a while, right, we continue to adapt and be agile to be able to take on the current and future challenges that we'll see. The next is, who are our customers? We have 80,000 customer sites in 150 countries. And nearly 90% of the top 100 Fortune 500 companies are SAS customers. Last is, how are we viewed by our peers? So for the last 8 years in the Gartner's Magic Quadrant for data science and machine learning platforms, we've been marked as a leader in that ranking. And in 2021, we've been marked as a leader across 30 different vendor rankings. So now that I covered who is SAS, now I want to talk about what we've done specifically around computer vision. And so with that, I have a couple of across-industry use cases I want to walk through. The first is we've worked with insurance companies to process images from dashboards to extract odometer readings. We've built models to analyze satellite photos to look for human-caused deforestation in the Amazon rainforest. We've used computer vision to identify queue formation, especially around checkouts, and then use that information to act accordingly to reduce wait times. We've helped manufacturer processes to look for placement of materials and to detect collisions in case that occurs. And since COVID, we've worked with organizations to help monitor for employee safety, especially in close quarter environments where we want to make sure people were adequately social distancing. And lastly, we've helped utility companies to process images from drones to capture what the vegetation growth is around utility lines, but then using that information to feed into what type of maintenance they should perform, optimizing their budget. So the key thing here is that all these use cases are different, right? Some of them process video in batch, some of them process real-time video. Others include additional techniques such as reinforcement learning and optimization. But what they all have in common is that they all use computer vision, running on SAS Viya, solving a specific business use case. So when we think about computer vision, right, there's really 2 sides of it when we look at the logical architecture. On the left-hand side, we have the model training aspect, and on the right-hand side, we have the model operationalization. In today's presentation is focused more on that right side of the model operationalization. And one of the key things I want to point out here is when we see this is that it's more than just scoring a computer vision model right, is that you really need this whole analytic pipeline to read in various data sources to do all the pre-processing necessary, but then also the post-processing as well to get to a decision or information to solve a business use case. And so to kind of highlight what that means today, I'm going to walk through one of our customers' use cases to highlight how we solve that in this paradigm. So this use case is walking through using computer vision and a manufacturing facility to prevent unscheduled downtime. So this business challenge and use case comes from our customer, First Solar. For those not familiar with First Solar, they're the largest manufacturer of solar panels in the Western Hemisphere. And what we're seeing here is a fixed camera looking down at a specific conveyor section on their continuous manufacturing line. So just to give you some context, what you're seeing here is that solar panels are exiting out of an oven on the left-hand side. It's moving along the conveyor belt and essentially going under what we call a broken glass detector. And what it's looking for is there any broken solar panels along the manufacturing line? And if they happen to be broken, they go into the dumpster, right? Otherwise, they're allowed to continue through the manufacturing process. And so the broken glass detector works pretty well, but there's some challenges with that because it's only at a single point in the conveyor line itself. And so what First Solar is seeing is that there's still some times where broken solar panels occur that's not captured that can cause jams. And so why that's important is because, as you can see here, if the solar panels break and they stay on the line, they can potentially back up all the way into the oven. And if they back all the way into the oven, that will cause a significant downtime event. Because at that point, you have to shut down the oven, clear out the glass, fix the issue, start it back up. And because this is a continuous manufacturing line, that means nothing else can be processed at that time. So what First Solar wanted to do was move to a computer vision solution to monitor real-time video. So you can see the video playing here as the solar panel is moving across the conveyor, and it breaks after the broken glass detector, so that one would have been missed. To monitor for those broken solar panels anywhere along the manufacturing line, so that once it's detected, it can send alerts, and it can send that both automatically into the manufacturing control processes, as well as operators for immediate action. So as we saw on the slide previously, model operationalization, is computer vision model enough to solve the challenge? And it's like the meme you might see, right? Like step 1, I have a computer vision model. Step 2, question marks. Step 3, profit. And it's really more than just that, right? We know that we need additional inputs to be successful for that computer vision solution. So with that, I believe there are 5 factors that need to be balanced and considered to have a successful computer vision implementation. So what we'll do is we'll walk through each of these and how that applies for this use case. So the first, this is pretty fundamental, is that we have to meet the business requirements, right? What is this solution trying to deliver that will generate value? So in this case, right, we can think about accuracy, and that's really decision accuracy, having enough confidence to know, what action to take for a given solar panel. And note that this is the overall accuracy of the analytic pipeline and not just of the computer vision model itself. And we'll talk more about that later in this presentation. The other is the latency. Because these panels are moving along a continuous manufacturing line, we need to be able to provide that decision quickly enough to make sure we're making the right decision on the right solar panel. Because if we act too slowly, what could happen is a panel is broken, allowed to move on, but then a good panel might be inadvertently scrapped, which would be bad. Next is having flexibility, because organizations like First Solar want to use computer vision to solve tough business use cases. And each use case will come with its own conditions and challenges. And it's important to have flexibility because, analytic pipelines may have multiple analytic techniques. They might have different analytic technologies, and you're not going to get there on day one. So the key thing there is having the flexibility to quickly add and modify without needing to rebuild from scratch is a key piece. So then that way you can quickly iterate and then also solve more than just one use case, not just going after just one particular item. So for this use case, we have a slide talking about our development journey, going over the different elements of the analytic pipeline we added to improve the accuracy over time to be successful. Next is integration. So I have an analytic, I could potentially create the model and run it offline, that's great. But unless it's going to somewhere where it'll drive value that's consumed, it's not gonna matter. So the key thing here is that we wanna make sure that the analytic inputs and outputs are in a place where they can be consumed and they're not going into a vacuum. So in this case, our target, because First Solar wanted an automatic process, is that we're going to send that information back into the manufacturing execution system so that they can take the automatic action with their controllers. And then costs are important as well. And this is important when we start to think about business implementation and justification, right? Because we want to make sure that we are investing for this use case, for future use cases, right? That is viable, we can continue to move forward. So you may think you see a problem, you start with the computer vision model itself, which is good, but you have to consider the cost aspect, which will include hardware costs, software costs, maintenance, retraining costs, because most likely you're not going to just deploy these computer vision models or these artifacts one time. You're going to do that multiple times. And so for this use case with First Solar, what SAS has done is we've proven that we can run this on one camera, and we're working with them to scale out to hundreds of cameras across multiple facilities. But the big thing there is we have a roadmap to do so, and we have a resilient and robust solution to do just that. And then finally, building on top of cost, it really just comes down to being able to execute and scale. So most computer vision efforts will usually start with a proof of concept, looking at one camera, but then you want to expand more and more. And then you're going to have all these computer vision models, the analytic pipelines that need to be governed and managed. As I mentioned previously, this is not a one-time exercise, because you're going to want to, you might have updated computer vision models, metadata, and other artifacts that you'll need to have available so that you can maintain and increase business value. So all these factors are considered in order to be able to meet both current and future business challenges. So this is something that First Solar will have to be able to invest. So if you get anything out of today's presentation, I present to you what I call the Teletubby slide, because when I put this together and reviewed it with others, that's what stuck up in my mind. So we'll walk through how we accomplish this for First Solar's use case. So high level, here's the analytic pipeline that we have using computer vision, as we showed the fixed camera previously, where you're reading that data, getting the images through an RTSP video stream, running the analytic pipeline with computer vision, sending those outputs through a REST API to a manufacturing execution system, and then that results going into a manufacturing controller for those familiar with PLCs for that automatic action. So let's see it in action. So on the left-hand side, we have the input video that's been cropped for that region of interest around the conveyor belt. And on the right-hand side, we see the output of the analytic pipeline, which is in turn passing information to the manufacturing execution system. And already we see one of the key advantages here of using computer vision is that we're able to provide coverage along the full manufacturing line to detect and classify solar panels rather than just one location. So let's explore the different elements, because there's multiple elements here with the model, the decision, the panel detection, and so forth that makes up this pipeline. So to describe the development journey, I would say we had three key areas for the analytic pipeline. We have the pre-processing, which may include any data augmentation we use for training the computer vision model. We have the computer vision model itself. For those familiar with computer vision models, we use the segmentation model. So what that means is for a given image, we are classifying on a per pixel basis of whether there's a solar panel present or not, and whether that's whole or broken. But because we don't output on a per pixel basis, we need to change or transform that pixel-wise classification to a panel-wise prediction that we can consume within the MES system. So we take care of that with our post-processing, which will show those elements in a minute. So we're able to take those elements and plot it to show our journey, because we added those over time to show how accuracy increased for this use case. So the first is we start with the segmentation model, processing an image of the full image frame that we got from those cameras. So we can see here we were able to gather everything. It worked okay. Next, we started to crop the images so that we're only focused on the region of interest, in this case being around the conveyor belt section itself. Next, as I talked previously, right, so here you can see an example of the analytic output from the computer vision model, where the green pixels indicates a whole solar panel and red indicates a broken solar panel. But as I mentioned, we need to change that, transform that from pixel-wise to panel-wise predictions. So the first thing we did is we did contour detection, right, to group similar pixels that can make an object. But what we see too is that because they're depending on your image resolution or how close those solar panels could be, that you might get contours that didn't make sense. So we added some dimensions that says, okay, here's a logical understanding of a panel, like a whole panel can't be bigger than this. So then that way, if there is any overlap, we're able to break them apart and say these are two different ones. As you may have saw when it's leaving the oven, you might see a partial one, so we had to be able to consider that. And then finally, for a given contour that you get, you might have mixed predictions. So that panel on the right will show that there's a mix of green and red panels, or pixels, sorry. So then we have to make a determination, when do we truly think it's broken or not? And in this case, I think we set it to 50% have to be present before it's considered broken. So at that point, we get from that pixel-wise to say, okay, we see these panels with these contours to determine whether it's broken or not in a given manufacturing line. On top of that, because we know the UNet model, the computer vision model, is not going to be perfect for every single frame that it processes, we added object tracking and time aggregation. So what that means is that we're looking at these panels over multiple frames. And what we're trying to say is, okay, if I've seen this panel 5 times, it's always said it's whole, and all of a sudden it says it's broken, I may not believe that initially until I see more predictions that say it's broken, and then I'm going to give it an updated label. So the whole idea there is that your computer vision model is not going to be perfect. So how do you add some type of persistence or confidence to allow you to have higher understanding of what's really happening? So that helps increase the accuracy. At the same time, you have to balance, like if you do that too soon, are you going to lose potential panels that you may not be able to pick up? So it's always a balance between the two. And then lastly, what we also did was we broke up the conveyor belt into sections, because the manufacturing execution system doesn't have any context of saying you're at XYZ on the camera. What it does understand, if I have a panel that's broken in zone 2 and it's been there for a while, maybe it's stuck, then I have to do a certain action. Or if it's in C3 and 4, it's moving quickly, then I automatically send it to the dumpster. So this is a way to simplify the information that will go into that manufacturing system so that they know what type of decision and action to take before on that solar panel as it's moving along. And then lastly, we saw a lot of variation throughout the process, so we did a lot of data augmentation techniques on the images to help increase the robustness of the model. So during this whole time, right, we were able to get feedback from our customer, right? We would try a model, run it, see how it worked, get updated information of what worked, what didn't work, get new training information. And so that was a good iterative process to learn, apply, and then re-execute. And at the same time, for First Solar's journey, they were new to computer vision, so we provided a lot of knowledge transfer sessions or information for them. So now that we've seen all these elements, how do we package them all together? So to package all these components together, we at the edge within First Solar's facility, we use a technology called SAS Event Stream Processing that's a part of SAS Via. And so if you're not familiar with what SAS ESP is, it's an analytic engine that's designed to process data continuously on the move in memory with high speed and low latency. So here we can see all those various components that we just listed in the previous slide, all consolidated together in a single analytic pipeline. So let me go over a couple of things that I think that makes this powerful. The first is that we're able to consume multiple input data sources, not just the video streams. And this is important, especially if you want to bring in other data sets such as industrial sensors, right? Like what's the manufacturing line doing at the same time that you might want to use with your computer vision model, vehicle telematics, et cetera. Able to score the computer vision model using hardware acceleration, such as GPU, with new technologies like OpenVINO and such as coming out and it's available. One of the key things, people may be more comfortable with Python. We see it as an extensibility. But the one great thing about this pipeline is that we have both SAS and open source working together, in this case Python, to do some of the contour detections and provide that information back so that we can execute. So in this case, we're using a SAS deep learning model to do the segmentation. But if an organization is more comfortable with PyTorch, Keras, TensorFlow, et cetera, they can easily incorporate that into this pipeline, especially with Onyx being available now that make it more natively easy to integrate. And then finally, because we haven't really touched on this yet, but latency matters. So we have a lot of built-in capabilities that's there to optimize that compute. So in this case, we have the resizing, geofencing, object tracking already built out and that we can take advantage of. And then finally, it just comes down to, where does the data need to go in order to get value? In this case, we're just writing the outputs into the manufacturing execution system. But if it needed to go to other dashboards or systems, we're able to do so to meet that need. So far, we've talked a lot about the analytic pipeline, all those components, how does it get packaged together? But another key thing is latency. So let's talk about why that matters for First Solar. So here, just to give you appreciation of the time scale that we see this, you can see the solar panel as it gets off of the conveyor belt moving through the line before it moves into the next process is about less than 5 seconds. And so there, we just want to make sure, right, that the decisions that we're making through that pipeline is fast enough to make sure we are doing the right decision on the right solar panel. And we want to make sure that we're not making wrong predictions. So to do that, what we do is we want to break down how long does it take to go through process one image, right? And we can see that in 3 key steps. The first is how long does it take to acquire an image from the RTSP video stream into the analytic pipeline? The next is how long does it take to run the analytic pipeline itself? But then once we finish it and we write out the results, how long does that take to get those results available to be able to take that action? And so a lot of this can be a function of the network architecture that's available at a facility, the hardware that you're potentially using, right, for compute capabilities and so forth. And then for this instance, we've proven out for the hardware that we're running at for solar, we can run the analytic pipeline in hundreds of milliseconds. But the key thing here is that we have the confidence to show these numbers, to be able to quantify them, so that First Solar has confidence in that these decisions are being available in that timely manner, especially as we start to scale up and scale out so that they can get a more distributed system. So now we're going to discuss how we would scale this analytic pipeline. So for starting a computer vision journey, right, most organizations would start with one camera, right, to prove out capabilities and so forth. But then we need a roadmap of how to scale that out to multiple cameras and facilities. So here's a depiction of where we are today with First Solar. And then once we've had that, once we're complete with that, we're going to start expanding to different cameras at the same facility. And what that's testing is multiple things, because we want to see how well does that computer vision model work in different areas. Do we need different models, different analytic pipelines, configuration to apply to different places? How much customization is needed? What about the performance, especially as we start to scale out to larger other areas? And then finally, we also want to go to other facilities to be able to replicate and use the same type of architecture. And so this isn't a one-size-fits-all, right? Like, I think there's multiple considerations for the architecture of what would be the right appropriate use. So like the number of cameras we want to target, what's the minimum required of frames per second we want to process to meet the business requirements? Because even though the cameras might be able to produce high volumes of data, we may not need all that for execution. And then we also wanted to consider other things like what does the CV model need and hardware, both in capabilities as well as cost. So what this is trying to show is that one of the benefits of using this type of architecture and plan and framework is that, SAS ESP and SAS VIA allows you to solve not just this use case for this particular item, but then to expand your investment to solve other challenges, both whether it's computer vision or not, to be able to help with their manufacturing process. So I'd just like to summarize what you saw today. One of the things I think that are the key takeaways for this presentation. So first is that the title of this presentation is how to operationalize and scale analytic pipelines with computer vision. Computer vision is important. Having high accuracy is there to make sure you're getting good, accurate information about it. But that's not enough to make that decision accuracy, accurate decisions for the process itself. So that's where you need the pre and post processing, be able to quickly iterate and add things as you need to. Latency is just as important, right? Depending on the business use case, right? How fast do you need to respond and so forth, being able to do that efficiently. We talk about technology choices and so forth. I mean, for us, it's about how do you accelerate these types of pipelines, whether it's built in SaaS, open source, et cetera, but then how do you make that available and to be able to execute. be able to leverage existing systems. Again, we want to be able to make this frictionless for the business, to be able to use these outputs without necessarily adding new tools or investments to get up and running, right? Because they want to, they want to get this quickly running for time to value. And then finally, just being able to execute and scale at the edge. And the key thing here is that we're all able to do this using SAS, and SAS enables you to use all these items and to accelerate your analytic journey. So that, I want to say first, thank you to the First Solar team for all the collaboration and work we've had with them, to my SAS colleagues for this effort. It's been very fun and informative. I know we have time for maybe a few questions, but if you do have any further, if you haven't stopped by the SAS booth, we're down on number 741. It's by the AI arcade, so if you want to play video games while talking, that is also acceptable. Perfect. I think we have time for a couple of questions.